This is the fastest man-made object ever created, racing to our sun at 700,000 kilometers per hour. Built to withstand drastic changes in temperature, it will be the closest a spacecraft has ever been to a star. So how did NASA prepare this record-breaking mission for its daring journey to the sun?
There are three main questions that Parker Solar Probe is going to answer. The first really is, why is the corona, why is it so hot? Why is the solar wind continually accelerated, and what causes these very high energy particles to be accelerated?
Dr. Nicola Fox led 5 research teams to launch this scientific quest in August of 2018, and one of the biggest challenges started with the size of the spacecraft.
With Parker Solar Probe, we had such a tight mass restriction to be able to be thrown away from the planet with the launch energy that we needed. That was a continual battle. A lot of missions, you solve problems by adding mass. You can make it bigger, you can grow something. We really couldn't.
The design of the probe's heat shield is considered revolutionary because it had to protect the instruments from extreme heat up to 1,400 degrees Celsius. And that was only half the challenge.
The Parker Solar Probe orbit goes very close to the sun on one side of its orbit and then out around the planet Venus on the other, taking that big temperature swing from incredibly hot to very cold out by Venus. As the temperature changes, the shape of the heat shield will change. It might become elastic or it could become brittle, but it's not going to be the same material that you had at the beginning. It will kind of potato chip. So we had to develop attach points that would be able to withstand the stress of the change in shape of the heat shield and also not allow any heat that the heat shield is absorbing to come into the spacecraft itself.
The shield was plasma sprayed with specialized alumina coating in a shade referred to as whiter than white, designed to reflect most of the sun's energy before it even reaches the shield. The result keeps the research instruments at about 30 degrees Celsius.
It is made of 2 carbon-carbon face sheets, and then they're very thin, and then there's about 4 inches of carbon-carbon foam that is between these 2 sheets.
That foam core is about 97% air, allowing the shield overall to only weigh 72 kilograms. Then it was put to the test.
We vibrate it, we make sure that it will withstand that very bumpy ride into space. But we also tested it to extreme heats. So we take coupons, which are like small sections of the heat shield, fully made up exactly as the heat shield would be, and then we can actually illuminate it with the same amount of energy that the sun will illuminate on the full heat shield. So we know that these small samples will withstand even greater temperatures than we will see on orbit.
Another crucial phase of testing was the spacecraft's autonomy system.
It takes light 8 minutes to travel from the sun to the Earth. And so if Parker Solar Probe has a problem, there's no way we can kind of joystick the mission from here on Earth. She has to be able to look after herself. And so it's almost like you think of every single thing that could go wrong on the mission, and you program her to deal with those problems.
The probe has sensors built around the main body of the spacecraft that are designed to never see the sun at all. If one does, the probe will know what necessary steps to take to reposition. On board the spacecraft are 4 instrument suites, carefully designed to collect data and withstand not only intense temperatures, but also radiation. Most unique of all is the Faraday Cup.
I always say the bravest little instrument on the spacecraft because it takes no shade from that heat shield.
The Faraday Cup takes measurements to determine velocity, density, and temperature of the sun's plasma. Made of refractory metals and sapphire crystal insulators, this cup was built to endure the full light, heat, and energy of the sun.
It has a little mini heat shield that is made of niobium C103. It is a pretty exotic instrument when all is said and done.
Dr. Justin Casper of the University of Michigan had the task of testing it for the mission.
And so they actually developed their own test chamber. They took reconditioned IMAX projectors, as it turns out that is the closest to all light that radiates from the sun that they could find. They put them inside a vacuum chamber and then basically illuminated the instrument and shot particles at it. And they could do that for as long as they wanted, and were able to fully qualify the Faraday Cup for Solar Probe. Every time something happens on the sun, that has an impact. It actually interacts with our planet's magnetic field and drives beautiful aurora. It can also cause problems for technology.
In 1859, a solar storm known as the Carrington event produced a coronal mass ejection that hit Earth's magnetosphere. It was one of the largest geomagnetic storms on record, shutting down the telegraph systems.
Losing the telegraph system for a few days was inconvenient. Losing the internet and our entire way of communicating, losing power grids, losing all the technology that we rely on now is a much, much, much bigger impact. When we have flown Parker Solar Probe, we will make huge, huge improvements in our ability to predict what is happening at our planet that is constantly driven by this star. It's not just about our sun. It's not even just about our sun's effect here on Earth. It's really about how stars throughout the universe work. We are really kind of fitting the missing piece into a puzzle. You can now put a real piece of physics into this sort of area where it's kind of like a black hole right now.
This episode was presented by the U.S. Air Force. Learn more at airforce.com. For more episodes of Science in the Extremes, check out this one right here. Don't forget to subscribe and come back to Seeker for more episodes. Thanks for watching.